In this series, what we're planning to do is extend upon what we've covered in the first 2 series, and that is we've looked at the heart, we've looked at a lot of the mechanical activities of the heart, we've also looked at the electrical activity of the heart and how it is that the heart is even able to sort of send these signals and perform its overall function. What I'd like to do now is sort of broaden our reach now and expand upon it. So the heart is essentially a pump, and the pump obviously needs some plumbing, it needs some pipes, and that's what we are going to be focusing on in this series. We're going to be focusing on blood vessels and looking at the circulation, so where the blood is indeed going and how it gets there. So when we're looking at our circulatory system, or when we're looking at our arteries and our veins, the composition between them is remarkably similar. So blood vessels essentially are comprised of 3 main layers, and these are called tunics. So the outermost part of the blood vessels, this is referred to as the tunica externa. Now, I'm going to be focusing on the beginning part anyway, on the arteries. We're going to be starting off with arteries, and then we're going to revisit veins. But an important thing to keep in mind, and this is relevant across many aspects of science and health science and nursing, is structure equals function. So what we can see here is that the structure of our arteries are very similar, and that's because their overall function is also very similar, and that is to, support the transport and delivery of blood. So looking at our tunica externa, this externalmost layer here, it contains a lot of collagen fibers in there, but it also has a lot of elastic fibers. So a good thing to sort of keep in mind here, or a good thing to remember, is that with our tunica externa, it begins with an E. E for elastic. So externa has elastic fibers. Now, as we zoom in and we look at our tunica media, this is the middle layer of our blood vessels. And with our tunica media, it has a lot of smooth muscle. So you can remember it as media muscle. And we're going to be talking about the function of these elastic fibers and smooth muscle fibers in a moment. Now, our tunica interna, this is our innermost layer of our blood vessels. And what's very important here is it is comprised a lot of epithelial cells. And epithelial cells are critical to ensure that nice laminal flow. And what laminal flow essentially means is that all the fluid is moving in the same direction. Now, turbulence is when fluid is moving in many different directions. So I want you to think of it like a river rapids, okay, when water is splashing and moving around. Now, if we're in a river rapid, cool, that's great. When we're looking at blood flow in the heart and around our body, bad. We do not want turbulent flow. We want nice, smooth, laminal flow. And that is where our epithelial cells come into play here. So 3 main layers: externa, media, and interna. External has a lot of elastic fibers. The media has a lot of that smooth muscle, and interna has that epithelial tissue to allow for that nice, smooth, laminal flow. Now, something I want to touch on here when we're looking at our circulatory system here is that it is a closed system. Now, what do I mean by that? A closed system is something where the beginning and the end are at the same point. So for example here, we start at the right atrium. We will move through the heart, and then it leaves the aortic arch and it goes through the entire body, okay? Getting smaller and smaller as we go from our arteries down to our arterioles, down to our capillaries. And it is in our capillaries here that we have that exchange of nutrients and fluid. We deliver oxygen, we accept CO2. Now, deoxygenated blood is returned back to the heart. This is what we mean by a closed system. Now, within this closed system, what we see is the arteries are moving blood away from the heart, okay, to deliver that, nutrient-rich and oxygen-rich blood to our tissues. Now, in our arteries, we have a couple of different types. We have our conducting arteries, and these have a lot of elastic fibers in them. And that's very important because it allows them to sort of stretch and then recoil. And that abides by the Windkessel principle, something we're going to talk about in a moment. So the conducting arteries are very much so like our really big arteries to ensure and allow that sort of consistent blood flow. Our distributing arteries, they control the degree of blood flow that go to particular areas of the body. And this is very important because we do not want 100% of our blood going to 100% of our body all the time. That's a massive waste of energy and resources. So what our body can do is that we can undergo vasoconstriction or vasodilation to control where the blood is going. So vaso meaning blood vessel, dilation meaning to dilate, to open, and then vasoconstrict meaning to constrict, to tighten in. And that was the importance of the smooth muscle that we saw in that tunica media. It really allows us to vasoconstrict or vasodilate. Then we also have our resistance vessels, and what this does is it allows us to control the amount of blood moving into the capillaries via peripheral resistance, and this is something we're going to be talking about in a moment. Now, when we're looking at our arteries and we're looking at the delivery of blood throughout the body, what is very important to note is that the further we move away from the heart and sort of the central axis of our body, our arteries are going to get smaller and smaller and smaller to ensure that our blood flow is consistent in terms of delivery around the body. So that's what we can see here by our sort of large arteries here, our big elastic arteries that can sort of stretch and really constrict in and move that blood consistently. We then have our muscular arteries, which, as I've said, will control blood flow to different parts of the body depending on the body's needs. So for instance, if I'm running for my life, I'm not going to turn around and go, I wonder how my breakfast is going in my stomach. I'm going to send a lot of blood to my GIT, like my intestines, to make sure that my food is being digested properly. No, not a priority. Blood is going to my legs so I can run like hell. Then we've got our arterioles, which again is just shrinking further down, with the overall objective being to get to the capillaries here, where we see that exchange of material. Now, talking about our capillaries, what is very important here with our capillaries is that they are tiny, they are microscopic, meaning that they cannot be seen with the naked eye. And it is in our capillaries that we see our arteries and our veins connect. So our arteries will sort of get smaller and smaller, going down to our arterioles here, and then it's connecting to our capillaries, which then connects to our venule, which is the smaller version of a vein. Venule will expand out, going to a vein, going back to our heart. Now, again, the most important function of a capillary here is the exchange of oxygen, the exchange of nutrients, and removal of waste from our tissues and any sort of waste in our interstitial space. So remembering, this interstitial space is the space that is surrounding your tissues. Now, there are three main types of capillaries that we need to talk about here. We have our continuous, we have fenestrated, and we have sinusoidal. So our continuous capillaries are the tightest, and we see them a lot in around our skin and in our muscles, and this allows sort of tiny solutes or fluid to move into our skin and muscles, but aside that, not much else. Our fenestrated capillaries are not as tightly linked. It almost looks as though someone's walked around with a pin and sort of poked heaps of little holes in it. And what that is that these are referred to as fenestrations. And that is allowing larger molecules to move out of the capillaries. And the main area where we see those are things like our kidneys for filtration, or in our intestines when we're trying to absorb those nutrients. So these are sort of bigger molecules, but nothing over the world huge. Now, our last one are our sinusoidal capillaries. These are basically, looks like they've gone through a shredder. There's much bigger holes here, and where we see these are typically in our liver and in our bone marrow or in our spleen. And these holes are big enough that sort of entire cells can fit through them. Now, with respect to this course as a whole, we will be focusing much more intently on these two. We will not be exploring sinusoidal capillaries in much greater detail. Now, as the blood is moving from our arteries down to our arterioles and then moving down into our capillary bed, where we see the exchange of nutrients and the exchange of materials to our tissue, what is then going to happen is that the blood is then going to flow through into our venules. Now, what is important to note here about the veins is a couple of things. One, the veins are known as capacitance vessels, and what that means is that a lot of the blood is actually stored in these veins, because you can see here, just purely in terms of the diameter, it's much wider than that of our arteries. The second thing is that by the time our blood gets through the capillaries and into the veins, we have lost a lot of pressure. So the venous system has a much lower pressure when compared to our arterial system, which is why the veins have a quite unique structure. They have valves. Now, how to remember this? V for vein, V for valves. Veins have valves. And the reason for these valves within our veins is the same reason as we had our valves in the heart, our, atrioventricular valves and our semilunar valves. What was the purpose of those valves in the heart? To prevent backflow. What is the purpose of these valves in our venous system? That's right, prevent backflow. So what's going to happen is as the blood moves from our capillary bed, moves up, and then as the blood wants to move down, these valves will snap open and prevent that backflow of blood. So we want to ensure consistently that this blood moves around one way only, okay? It is a one-way road throughout our circulatory system. Now, this low pressure system, depending on what you as a person are doing, can sometimes get you into trouble. I'm sure we're all familiar with some stories of guards or soldiers that are standing at attention for a long period of time, and then suddenly they'll just pass out. And the reason for that is because the venous system has such low blood pressure that if you are standing still for a very long period of time, due to gravity, you cannot get enough blood returning to your heart to ensure adequate blood flow. So this is where we have two main systems in place to help us with that. The first one is called the skeletal muscle pump. And what this is that because our veins have valves that snap closed, preventing the backflow of blood, what can happen is as you're tensing your skeletal muscles, again, especially in your legs, what will happen is that those skeletal muscles will press on your veins and push that blood up, ensuring adequate blood flow. The second system here is our respiratory pump. And what this involves is using your lungs and your abdominal muscles to push and squeeze the large veins that we have in our thoracic cavity to again help push that blood around and to the heart. Both of these systems, our respiratory pump and our skeletal muscle pump, are also used extensively by fighter pilots, people who are undergoing a huge amount of G-force, which is pushing the blood away from their brain or away from their heart. They use these skeletal muscle pumps and respiratory pumps to push the blood back to the heart, ensuring that adequate circulation is involved. So looking again at our circulatory system, comparing our arteries and veins, or arterioles and our venules, they are both very similar in their overall structure because they are both very similar in terms of their overall function, which is to say the delivery of blood around the body.